Hello guys, how are you doing? From Ash here. Today I would like to solve a problem, quite a classical problem. It's the catenary, yeah? So the catenary is a curve that is traced by change. If you put a chain that is fixed in two points under the action of its weight, then the chain will draw a curve, yeah? And this curve is the catenary. Yeah? So we will assume that the only forces on the chain are the tension and the weight of the chain. Yeah? So then we will use some coordinates, x coordinates and y coordinates. Yeah? So here we have an element of this ideal chain. So here we have this infinitesimal element, yeah, of length ds under the action of the tension, and its weight. Its weight will be dm times the acceleration of gravity. Yeah. So dm, we will introduce the linear mass density mu times ds, the length of the element. Yeah. And so yeah, now we are ready to go. So first we will name some points. So well, the fixed point on the left will have coordinates xa and ya. The point in the middle will have coordinates xm and ym. This is actually the minimum of the curve. Yeah. So it's the lowest point that of the chain, and or the coordinate is the right extreme. Yeah. So xb, yb. Then we will consider only this part. Yeah. So x belonging to xm, xp, and y belonging to ym times yv. Yeah, this is a simplified thing because here the curve has a positive slope, so things will be nice then. But then the calculation will be applied to all the curve. So first, the length of this part of the chain will be L equals the integral of ds, between xm and xp, in which ds is square root of dx square plus dy square. Yeah. So yeah, well, in this case we can factor. We are assuming that we are working in the x coordinate as a independent variable, but we will do a trick here. We will use instead the y coordinate as a independent variable. Yeah. So we will write instead L equals the integral from ym to yv of the dx square plus dy square, where we are assuming that x is a function of y. Yeah. Then we will factor dy. So we will get finally x prime square dy. Yeah. So this is the trick. Why we then we got x equals x of y. Yeah. Yeah. So then and this L is fixed. Yeah. It's the length of the chain, so it doesn't change. Yeah. So we will get another page. Oh, thank you. So now we will write the potential energy. This will be U equals the integral from Ym to Yv of the weight of the differential elements times its height. Yeah. So this is the potential energy. So this now we will write it as a function of the differential elements of distance. So integral from Ym to Yb of mu ds, this is dm, times g times y. So we will factor the mu and g outside times integral from Ym to Yv of y ds. Yeah? And finally, we will write the ds as a function of the coordinates. Yeah, integral from Ym to Yv of y square root of 1 plus x prime square dy. Yeah. So then we want to minimize the potential energy. Yeah. So we have something that depends on a curve. Yeah, an integral that depends on the shape of the curve of x of y. So we will have to use the variational principle. Yeah, but we have a constraint. The constraint is that the length of the chain is fixed. Yeah, between Ym and Yv. So then we will write an action. Yeah, so S equals y minus mu g l, yeah, times the Lagrange multiplier. Yeah. Yeah, so we use this mu g here to, so this expression has the same units as the potential energy. Yeah, so in this case lambda must be, the Lagrange multiplier must have units of distance. Yeah, so here we have the lambda is the Lagrange multiplier. Yeah. So let's see what is the expression for S. So S will be mu g. We will factor the mu g's. Yeah. So integral from Ym to Yv. Yeah, so we have a y here. Y minus lambda here times 1 plus x prime square dy. Yeah? So now we are ready to go, because from this action we can get the Lagrangian. Yeah? So now this will be the Lagrangian. So the Lagrangian in this case is the Lagrangian of L of y x comma x prime. Yeah, but here we will see that the x does not appear explicitly, so it's just L of y comma x prime. Yeah, so this will be good. Then we know that when we want to solve this kind of variational problems and we got the Lagrangian, we got to use the Euler-Lagrange equations. Yeah, so the Euler-Lagrange equations is the following. Yeah, so in this case, as y is the independent coordinate, the Euler-Lagrange equation is d to the y of the L to the x prime minus the L to the x equals 0. Yeah. So in this case, we already saw that the L does not depend on x. Yeah, so explicitly, so this term here will be 0. Wow! Wow, very nice. Yeah. So we just have to we got that d to the y of the L to the x prime equals 0. So as this the derivative of this term is equal to 0, then we got that the L to the x prime equals a constant. Yeah, let's call it c. Yeah, now we will remember the expression for L equals y minus lambda, the Lagrange multiplier, times 1 plus x prime square. Yeah, so now we take the derivative with respect to x prime. The L to the x prime equals, we got the derivative of the square root here, so we will get 1/2, but the 1/2 will cancel with the derivative of the square here, so we will have y minus lambda. The derivative of the square root is 1 over square root. Yeah, and the 1/2 that cancels with the derivative of this term here. Yeah, wow, now we are advanced a lot. Yeah, so we will move the video page assistant, please. Oh, thank you. So then we got that this term here equals c. Yeah, so we will make an extra step here. So we can replace the x prime. So this is the same as y minus lambda dx to the y 1 plus dx to the y square equals c. So now we can multiply this part here by the y to the x. So we will invert the independent variable. Yeah. So here all the same, dy to the x. Yeah. So this here will cancel, and this we will multiply inside. Yeah. So finally we get y minus lambda over, when this term will enter into the square root, it will enter as the square of dx to dy to dx. So we will this term will cancel to 1, and then we will get y prime square. Yeah. Yeah. So now we will do the following. We will to simplify this differential equation. We will replace y minus lambda by a new variable. So we will say u of x equals y minus lambda. So we will make here. If you notice now, the independent variable is x now. Yeah. So we got now that y equals y of x. So now we can see that easily that u equals y prime. U prime equals y prime. So then we got u over square root of 1 plus u prime square equals c. Yeah. So we will get another page. That equation is very well known. Yeah. You can easily see that the solution is a hyperbolic cosine. Yeah. So we will write it again. U over 1 plus u prime square equals c. Yeah. So we can check that u equals alpha with alpha constant. Yeah. Hyperbolic cosine of x minus x0 over alpha is a solution to this equation. Yeah. So let's check. We got that u prime will be hyperbolic sine. Yeah. So we got 1 over alpha that will cancel this alpha. So will be hyperbolic sine of x minus x0 over alpha. So then 1 plus u prime square will be 1 plus hyperbolic sine of x minus x0 over alpha square, and this is just hyperbolic cosine square. There. So then when we calculate u over the square root of 1 plus u prime square, we will get alpha hyperbolic cosine of x minus x0 over alpha over the square root of hyperbolic cosine to the square. So this will be the module of hyperbolic cosine, but the module of hyperbolic cosine is always positive, so it's just hyperbolic cosine. Yeah, and this will cancel. Yeah, so this is actually a solution if alpha equals c. Yeah, so alpha equals c, and the solution is u equals alpha hyperbolic cosine of x minus x0 over alpha. Now we will remember that the curve, the minimum of the curve is x when it is at the xm point. So it necessarily means that the x0 equals xm. Yeah. So finally, we can write u equals c times hyperbolic cosine of x minus x m over c. Yeah. So we will motivate the page, and then we will remember our variable u. U equals y minus lambda. So y, that is our original coordinate, equals u plus lambda. Yeah. So finally, y of x equals c times hyperbolic cosine of x minus xm over c plus lambda. And this is the solution. Yeah, so, well, lambda in this case will determine it will be necessarily lambda of ym minus c. Yeah, because hyperbolic cosine of 0 when x equals xm is 1, so we got a 1 here. So then if we can get that this expression here. Yeah. So and then the c constant you have to determine it from the attachment points of the chain. Yeah. So well, this is the answer. Yeah. So is the catenary is a hyperbolic cosine curve. Yeah. This expression can be derived from in several ways. But I like this one. I think this is the neatest one for this curve. Okay, guys. I hope you like it. See you. Bye.